Students, very good afternoon to one and all. Good afternoon, Sakshi, Sanika, Vaishnavi, both Vaishnavis, Jyoti, and Chandana, Mahek, Rutuja, Sunil. Hi. Good afternoon, students. Good afternoon to all of you. So, we have been discussing the chemical kinetics for long, right? So, I think today we will complete this chapter. Okay, I mean the theory part we may complete today. Okay, so we'll try for that. So in yesterday's class, what we have discussed, so mainly we have discussed about the factors affecting the rate of the reaction. Okay. So totally, how many factors were there? How many factors were affects the rate of the reaction? Can anyone tell me the number of factors which affects the rate of the reaction? 5. Very good. So what are those 5? What are those 5? What is the first one? What is the first factor we have studied yesterday? What is the first factor? Very good, Sakshi. It is concentration. So concentration, how does it affect the rate of the reaction? If I increase the concentration, what will happen to the rate? Will it increase or it will decrease? Concentration is indirectly proportional relationship. Or yeah, very good, Mahik. It is increasing. So they are directly proportional to each other. And what is the second factor? What is the second factor? Surface area. So surface area means nature of the reactant, right? So if the surface area is more, rate of the reaction is more. So again, they are directly proportional. What about the temperature? What about the temperature? The third factor is temperature, whether it is directly proportional or indirectly inversely proportional to the rate. Temperature is directly proportional, no? So if I increase the temperature, rate of the reaction will also increase. Yeah, very good. So, in this under this temperature topic only, we have discussed one more very important formula, and we call that formula or that equation as Arrhenius equation, right? So, what is Arrhenius equation? That is very difficult to type. No, I'll give you. So, the Arrhenius equation, which we have studied yesterday, is nothing but K is equal to A into E power minus EA by RT. Okay, you should not forget this. Now, you guys are going to give me the terminologies. Okay, yesterday I have shown you the same slide, right? So now you guys tell me what is K here. First let's start with K. What is K here in this Arrhenius equation? K denotes what? What does this K denote, sir? We have been studying this now from the beginning of this lesson. From the integrated rate equation, from the rate concept, we are studying this K. Very good. It is a rate constant. Very good. K is nothing but a rate constant. What is EA? What is EA? What is EA? EA is called as? EA is called as what? Very good. It is activation energy. Energy of activation. Very good. What is R? What is R? You should keep everything in your fingertips. No? Yesterday only we have discussed this. Yeah. R is nothing but the gas constant. Very good. R is a gas constant. What about T? T is very easy, no? T is nothing but the, what is T? Yes, it is temperature. T is temperature in Kelvin. Very good. Yeah. What is A? What is A here? What is A here, my dear students? Yeah, frequency factor or Arrhenius factor or pre-exponential factor. So these are the terms which denotes the rate of, the Arrhenius equation. Okay, fine. So, and also I have shown you one diagram, okay, with reaction coordinate versus potential energy. Okay, this is the potential energy curve, and if I'm having a reactant, suppose if I take H2 plus I2 giving 2HI reaction, H2 and I2 will be the reactant. Okay, and the reactant will be converted into hydrogen iodide product. 2 moles of hydrogen iodide is formed. So this is the pathway that this reactant will take to reach the product. Okay, so this is the potential energy of the reactant line, and this much of energy is required for the reactant to get activated. So which is nothing but the activation energy for those two molecules, and after getting activated, it immediately gets converted into the product 2HI. Okay, and the difference between the reactant potential energy and the product potential energy is called as delta H, which is called as enthalpy of the reaction. So this is the potential energy curve for H2 plus I2 giving 2HI reaction. Okay, so all these points are very, very important because in the numericals, you will get questions from numericals, okay, from this concept. So what they will do, they will give delta H or they may ask delta H. Okay, so you should be able to find out. They will give you two energy value and they will ask you to find out the delta H. So in that case, what you have to do? You have to subtract one from the other. Got it? So these points, the theory point of this Arrhenius equation is very important. You should be able to understand this and apply this to the numericals. Okay, according to the question. Clear? So this is what we have discussed yesterday. And also I told you all the molecules in the reacting species, they do not have the same kinetic energy because the mass of each particle will differ, velocity of each particle will differ. Half mv square is nothing but the kinetic energy. So kinetic energy will also differ for each reacting species. Okay. So two scientists, Boltzmann and Maxwell. So they suggested the behavior of large number of molecules. Now let's see their concept. Okay. Yesterday I have showed you Boltzmann and Maxwell picture. So here the topic is Maxwell-Boltzmann distribution of molecular energy. Okay. Here we are going to see a graph. Okay. In the y-axis we are taking fraction of molecules. Fraction of molecule means it is Ne by Nt. And in the x-axis we are taking the energy. Okay. So now, first of all, I am getting a curve like this. Okay. And this is the point, or I can say this point as most probable kinetic energy. The peak position of this curve denotes the most probable kinetic energy of that molecule. Molecule is there, and the peak position of the curve denotes the most probable kinetic energy of the molecule. Okay. And let me take this point on x-axis as EA, which is called as activation. So this is the activation energy of that molecule. Okay. So in this area, if you see some fraction of molecules, they have the capability for collision. Okay. Fraction of molecules will be present there, which are capable of effective collision. Because once the molecule gets activated, they will collide with each other, no? So in that area, so some of the molecules are colliding with each other. Got it? So now I am taking this particular temperature as T1. Okay. So this is the curve I am getting for that particular species with the temperature T1. Okay. Suppose if I take that T1 as, 300, we can take 300 Kelvin as T1 value. Okay. So now what happens? Now you see, I am getting one more curve with blue color line. So this curve is with respect to temperature T2. So if I increase the temperature or if I decrease the temperature, so what is happening? not with increase or decrease. If I change the temperature from T1 to T2, the curve position is also changing. Now you see the difference between two curves. So T1 is having the highest peak position compared to T2. Okay, so this is the graph we observe for fraction of molecules versus the energy for two different temperatures. Okay, so the energy is getting distributed, and now the activation energy is raised for T2. Okay, so you see the activation energy, it has got increased now. Now in this area, some of the fraction of molecules, they are having the capability to for effective collision. Okay, clear? So if I change the temperature, fraction of effective collision undergoing for each molecule will also differ, and the activation energy will also differ. Okay, so because in Arrhenius equation we have e power minus EA by RT. Okay, EA and RT. EA divided by RT. Okay, activation energy is increasing if I change the temperature. Got it? Clear for all of you? And also if you increase the temperature, the rate of the reaction will also increase. Rate of the reaction will also increase. That is what is observed here in these two curves. So if I increase the temperature, suppose let me take T2 is greater than T1. Okay, if I increase the temperature, the number of molecules getting collided, that will also increase. No, number of collision will increase. So rate of the reaction increases. Got it? So Boltzmann and Maxwell, they observed this and they gave this distribution of molecular energy curves for a certain molecule. Clear for all of you? Shall we move on to the fourth factor which affects the rate of the reaction? Shall we go with that? Yes. So Sakshi is asking a doubt. If temperature increases, then activation rate. Dear, what is activation? Activation energy? You are asking about activation energy. Activation, yeah. See, if I increase the temperature, rate is also increasing. Means activation energy will be decreased. Means the molecule will get activated easily. It will get activated soon. If the temperature T1 is taken as 300 Kelvin, okay, the activation energy for that particular species may be what to say 50 kilojoule. Okay, and if I increase the temperature, what is happening? The reaction is happening very fast. Rate of the reaction increases, means the activation energy is getting decreased. Activation energy is getting decreased. I'll show you with the curve. So this is a curve for reaction coordinate versus potential energy. Okay. So if I'm taking this as the activation energy for T1. Okay. Activation energy for T1. And if I increase the temperature, what will happen? The molecule will be activated easily. So this is the activation energy if I increase the temperature. Clear? So the molecule will get activated as soon as possible if I increase the temperature. So on increase the temperature, activation energy and temperature, they are inversely proportional. So that is a relation. Got it? Very good. So now we are moving into the fourth factor, which is the light. So from the light, what we get? We get h nu, amount of energy, right? So which is nothing but the packets of lights. H nu is called as the packets of light in the form of photons. If I increase or if I do the reaction in presence of light, the rate of the chemical reaction is considerably increased by the use of certain radiation. If I use the light energy or if I give some light energy to the system, rate of the reaction increases. So this is what is happening in photosynthesis, no? Okay. So if h nu amount of energy is absorbed by the system, then the rate of the reaction also increases. Got it? And also, Here in this picture, you see person with the telescope. Yeah. Now we are moving to the fifth factor, which is called as catalyst. Can anyone give me the definition for catalyst? Have you heard of this term catalyst in your 11th class or in 10th class, etc., etc.? In your previous classes? What is a catalyst? Which is used to pass in the reaction. Okay, very good. Very good, Aisha. But I'm seeing Aisha today only, I think so. Where were you for the past few days? Suhana, Aisha, you guys are new to today's class or what? Okay. Anyways, welcome you all to this 12th class, the new students. Yeah, let's come to the topic. Aisha, you have already attended my 11th class, no? I think so. Have you attended? Yes, the same Aisha, you are right. Okay, okay, fine. Okay, my dear, okay. Yeah. Let's come here. Sanika has given me the definition. So Sanika has said that it is a substance increase the rate of the reaction without participation. Very good. Sanika, your definition is also correct, exactly right. And Sakshi is saying that it increases the rate of, very good. Sakshi, good. Mahik is saying that substance is increase rate of the taking part in Mahik. So all of your definitions are exactly correct. Okay, 100% correct. So a catalyst is a substance. A catalyst is a substance that alters the rate of a reaction, but is found to be chemically unchanged at the end of the reaction. Means it will only change the rate of the reaction. It will only increase the rate of the reaction, but it will not take part in the reaction. It will not participate in the reaction. Okay, so those substances are called as catalyst. So what they are doing? So the catalyst provides an alternative pathway of lower the activation energy. So what a catalyst is doing, it is changing the pathway for a particular reactant by decreasing the activation energy. Okay. Sorry. Yeah, I'll show you. I'll show you how it is decreasing. Okay, how it is lowering. So let's take reaction coordinate and potential energy curve. Say, suppose, let me say that I have a reactant here and a product here. Reactant is getting converted to a product. And you see here, a person is starting his cycling here and trying to reach the end product. So now, if this is the case, without catalyst, this is a case without catalyst. Now, if I add the catalyst to this reactant, the pathway will differ. Okay, you see the blue color pathway. So what is the difference? So a person is starting here and reaching. You see here how this person is going. He is going very easily, no? So he reaches the products earlier. He reaches the product early. So in without catalyst case, what is the, I'm sorry, in the without catalyst case, what is happening? So he is spending most of its energy and then only he is reaching the product. But if I use a catalyst, the pathway is changing and the person is able to reach the product so easily. He can attain it can go to the end point so easily. So a catalyst is altering the rate of the reaction. And how does it alter? By decreasing the activation energy. By decreasing the activation energy. So this is the activation energy or energy of activation without catalyst. And this is the energy of activation with catalyst. Got it? Clear? Very easy. Very easy. Yeah, sorry students. So can you able to understand? Can you able to understand the concept? Catalyst is altering the rate by decreasing the activation energy. That's all. Very easy and simple. Yes. Okay, Millie. So with this, we are completing the factors affecting the rate of the reaction. Now we will solve some questions, okay, from the light concept, from the catalyst concept and all. Okay. Now the first question is, a catalyst is a substance that lowers, very easy, no, potential energy, activation energy, kinetic energy, none of this. What is the answer for this question? Yeah, it is obviously activation energy. So now you guys are giving me the answer. If I complete the entire 12th class chapters and if I ask you the same question at the end of this year, will you be able to tell? I hope you guys will tell. I hope. Okay. Yes. That's great. Good. Yeah. So let's move on to the next question. Which of the following will provide an alternate path of of lowering the activation energy? Which of the following will provide the alternate path? Reactant, solvent, catalyst, intermediate.
Catalyst.
Very good, Vaishnavi. It is catalyst. Very good, students. It is. Yeah. So now we'll go with. So two questions are enough for from this catalyst part. So now we will move on to the last topic of this lesson. Okay, which is called as collision theory. Which is called as collision theory. Okay. So, what are the requirements for a reaction? If a reaction has to happen or if a reaction has to occur, what do we need? What do we require for a reaction to happen? Suppose you take, we have two reactants. So, what are the requirements for a reaction to happen between those two reactants? Can you think of it? Already we have discussed this in yesterday's class, I think. I have given some few informations about this in yesterday's class. Okay, I'll tell you. So if a reaction has to happen, Mahek is saying collision. Okay, that is absolutely correct. So two molecules should collide, right? Two molecules should collide with each other. So you see here, they should collide with sufficient energy. Second point is they should collide. Two molecules should collide with some sufficient energy. So then only a bond is formed between the two molecules because of this collision. Okay, very good. So the two requirements are first should the molecule should collide. Second is they should collide with sufficient energy. Okay. Now collision theory was developed by Max Strauss and William Lewis in between 1916 and 1918. Okay. And in the collision theory, if you see the concept, the theory is based on the kinetic theory of gases. So this kinetic theory of gases topic was discussed in the states of matter lesson of your class 11. Okay. But unfortunately, that lesson was deleted for you, okay, from the last year. So it was discussed in that under that topic. Okay, you don't have to worry. It is very easy only. Okay, so in that theory also we would study some informations about this collision, and in this collision we are going to see some informations about that theory also. Okay, so basically this collision theory is based on the kinetic theory of gases. Now let's see the assumptions of collision theory. Okay, so first of all, in the collision theory, all the molecules are taken as hard spheres. All the molecules are taken as hard spheres. Okay, suppose if this is a molecule, if this is a molecule. So each molecule is taken as a hard sphere. Okay, so this is the first assumption. And the second assumption is the reactions occur when the molecules collide. So if two molecules come closer to each other, what is happening? So they are colliding with each other. Okay, they are colliding with each other. And because of this collision, a reaction is happening between the two molecules. Okay, between the two hard spheres, a reaction is occurring. Okay, so these are the some of the assumptions. Now, if I increase the temperature, for that molecule, so what will happen? Average kinetic energy of the molecule increases. So this is what we have discussed in the factors. In the temperature factor, we have discussed this. If I increase the temperature, molecules will move here and there. So velocity of the molecule increases. So in the half mv square formula, as the velocity increases, kinetic energy also increases. So this is what we have discussed yesterday. So average kinetic energy of the molecule increases. So if the molecules moves very fast, so what is happening? Number of collisions per unit time also increases. So on increasing the temperature, two things are happening. One is kinetic energy is increasing because of the speed, and the number of collisions are also increasing per unit time if I increase the temperature. Okay. And if you observe this very carefully, this increase the rate. This thing increases the rate. So these two, kinetic energy and collisions are increasing, no? So these two things increases the rate of the reaction only by 3%. Okay, kinetic energy may increase, number of collisions may increase. So because of these two, rate may increase, but the rate of the reaction increases by these two factors only by 3%. Okay, hence what happens? The increase in rate of the reaction is not simply due to the increase in the collision frequency. So the increase in the increase in the rate of the reaction is not only by the collision. So there is some other factor which is associated with this. So we'll see to that. So did you all understand? So do you have any doubts so far from the collision theory part? So everything what I have discussed so far is clear now for all of you. If you're having any doubt till now, till this slide, you can ask me. If there is no doubt, let me know in the chat box. I will move on to the next slide.
No doubt.
Okay, what about others? Yeah, it is clear. Okay, my dear. Good, Aisha. Very good. Okay, okay, Sakshi. Yeah. So now we have to think of the factors which depends on the rate. Okay, so the rate depends upon, first of all, collision frequency, and also it depends upon the effective collision. Okay, so far we have been studying only about this collision frequency. So the rate increases because of this collision frequency, but only by 3%. Okay, so the other factor which affects the rate is effective collision. Okay, effective collision. So what is meant by effective collision and what is meant by collision frequency? So now we are going to study about these two terms in detail. Okay, so I'll go in order. So I'll start from collision frequency itself. Collision frequency is denoted by the letter Z. Okay, now let's see the definition for this. It is the number of collisions that takes place per second per unit volume of the reaction mixture. So what it is? The number of collisions that is taking place in a container per second per unit volume is called as collision frequency. Okay, for bimolecular gaseous reaction, bimolecular means if only two reactants are present in your mixture, then this collision frequency Z is of the order 10 to the power 25 to 10 to the power 28. So some values. So Z is denoted by some values. Collision frequency is denoted by some values for certain reaction. The definition is number of collisions taking place per second per unit volume. Okay. So this is collision frequency. all the collisions of the reacting species at a given temperature are not effective. All the collisions taking place in a reaction at a given temperature are not effective. They will not undergo, all the molecules will not undergo effective collision. Suppose if I have 10 molecules, so 8 may undergo effective collision, but 2 may not undergo effective. They may undergo ineffective collision. They will not collide properly. Okay. So we cannot say that all the molecules have collided with each other and all the reactants have been converted into product. No, that kind of story cannot be said. Okay, because some of the collisions are ineffective. If all the collisions are effective, the reaction must be very, very fast. If all the 10 molecules got collided with each other very effectively, then we would say, or we can say that reaction must be very, very fast. But in actual practice, practically, if you see, most chemical reactions take much longer. All the reactions will not take place very fast. They will take some time. Most of the reactions take much longer time to get completed. So what is the meaning? They did not undergo, all the molecules did not undergo effective collision. So that is the meaning we are getting from, or the concept which we are learning from this collision theory. Got it? So all these things are the theory part. Students, can you able to understand? Collision frequency part is clear to all of you now. So what are the points? Definition is important. Number of collisions taking place per second per unit volume is called as collision frequency. All the collisions are not effective. So if they are effective, then the reactions should occur very fast. But in practical, all the reactions will take more time. Means they will not occur very fast. Means some of the molecules will undergo ineffective collisions only. So any doubt so far? Clear, right? Okay. Now we'll move on to the second factor, which is called as effective collision. Now, the basic requirement of collision theory is that the reacting species must collide. So, this is what we are seeing from the beginning of this collision theory, right? So, if a reaction has to happen, then the two molecules must collide with each other. And also in the last collision frequency concept, we have discussed that only a very small fractions of collision is effective. Only a small fractions of collision is effective and we call that as effective collision. Okay, so what is effective collision? More or equal to threshold energy. I'll tell you what is threshold energy. Okay, so effective collision will be more or equal to the threshold energy. Actually, threshold energy is the minimum amount of energy required for a molecule to get ejected. So we will see this threshold energy in the next slide in detail. Now, if the energy of the reacting molecule is less, for an effective collision to happen, the energy should be more or it should be equal to threshold energy. If that energy of the reacting species is less, okay, then the collisions will be ineffective. Okay, the collisions will be ineffective. If the energy goes less, then the collision is ineffective. Now let's come to, let's study some more information, and then we will move on to threshold energy. So thus the energy of collisions determines the possibility of the reaction. How does the energy determines the possibility of the reaction? If energy is very less, energy of the reacting species is very less, then this denotes the ineffective collision. It denotes the ineffective collision. If the energy is more or if it is equal to the threshold energy, then it will lead to the effective collision. Okay, so this is how the energy is determining the possibility of a reaction. Got it? Now let's go with threshold energy. The colliding molecules should possess a certain minimum amount of energy to give the product, and this minimum amount of energy is called as threshold energy. So the reacting species should have some energy, some minimum amount of energy to get reacted with each other, and we call that minimum amount of energy as threshold energy. Okay, so the definition for threshold energy is very important. So you can take down this. Shall I move on to the next slide? Okay, yeah, just give me a second. Yeah, now we'll go with the requirements for a bimolecular reaction. So if two molecules are reacting with each other, what are the requirements we have for that? First of all, the collision between the reactant molecules, as I have already told you, they should come closer to each other and they have to react with each other. And the next is the energy requirement, which is called as activation energy. I told you, no, if a reactant has to get converted into a product, then some amount of energy is needed to get activated for that reactant. And we call that as energy of activation or activation energy. Okay, then only a reactant can be converted into a product. Okay. And third is orientation of reactant molecules. What is the first factor? Collision. Two molecules should collide with each other. Second is energy. Minimum amount of energy is required to get activated. Third is orientation of the reactant molecules. So what is orientation? Suppose if I take AB plus A2B giving AB2 and A2. Okay, so I have two reactants and two products in this reaction. And these two are the reactants, A2B and AB. Okay, so this A2B is the first one and the AB is the second one. Okay, so these two are the reactants. They may collide with each other. They may come and get oriented in the same direction. You see here, they are getting oriented into the same direction, and the collision is happening and the product is formed. Okay, and the product is formed. Now you see to the products. Reactant and product, they are same. Reactant and products are same, no? We have got the same A2B and AB. So if this is the case, then we can say that the collision is ineffective because the orientation is not proper. Orientation of the reactant molecule is not proper. The two reactants did not get oriented properly, so that's why it leads to ineffective collision and it doesn't lead to the formation of a proper product. Okay. But if you see for the effective collision, the same reactant A to B I am taking. But now, in the previous case, we had A here and one more A here and B here. But now here in this case, you see, we have B at the last. Now, this A to B and AB, they are reacting with each other. They undergo collision and they lead to the formation of products. Now you see here, what is formed? A2 and AB2. This is A2 and this is AB2. So the desired products are formed. Means this molecule, these two molecules have undergone the effective collision because of the proper orientation. Okay, clear? So the orientation is also very important. Okay, if the molecules do not get oriented properly while colliding, so even though the collision may happen or occur, the desired products will not form because of the result of ineffective collision. So can you all able to understand the picture and the concept regarding this orientation? Do you have any doubts? I'll also explain this with one example. Okay. Yeah. Okay, Sakshi, very good. So we'll take one compound. We'll take methyl bromide. Here, carbon is partially positive and bromine is partially negative because bromine is more electronegative atom, no? So it takes the negative charge and carbon is taking the positive charge. And to this molecule, OH minus anion is or the nucleophile is coming and reacting. Okay. So if these two reactant react with each other, we would get two products. One product is from the improper orientation. If the orientation is not proper, then if the two molecules come closer to each other, they will repel each other like this. This is one of the product. Okay, no products are formed from this. And if the orientation is proper, from the proper orientation, we get an intermediate. Okay, and the intermediate will break down to give the corresponding products CH3OH, methanol and Br minus ion. So what is the correct proper orientation? If this OH minus comes in the same direction where the Br minus is also there, then the products are not formed. They are getting repelled with each other because both are negatively charged. Br is also negatively charged, OH is also negatively charged. So like charges will repel each other. Okay, so improper orientation leads to no product. And now in the proper orientation, you see OH is coming from the other side. OH is coming from the back side to this carbon. Okay, so where the positively charged carbon is there, to that side, the negative is coming. So positive and negative will attract each other, and because of this, we are getting a product from the intermediate. Clear for all of you? So orientation is also proper. Very important. Okay. Yeah. So after this, we'll see potential energy barrier. So let me take B and AC as the reactants. So these two reactants, they are reacting with each other and they are leading to B and C products. Okay. So now, for this reactant to get converted into this product, they go with an intermediate. Okay. BAC. And this is called as intermediate, or we can call this as activated complex also. When two molecules, when two reactants come closer to each other, they will get activated at one point. No, so the activated species looks like this. This is the activated complex. So all the atoms require energy to overcome the repulsion between B and AC. So if B and AC come closer to each other, there will be some repulsive force. So some amount of energy is required to overcome that repulsive energy, that repulsion. Okay, so that energy comes from the kinetic energy of the colliding particle. So from where does that energy which is required to overcome the repulsive energy comes from? From the energy, kinetic energy of the colliding molecules. So kinetic energy of the colliding particles is converted into the potential energy in activated complex, and we call that intermediate as transition state. Okay, so that is nothing but the potential energy barrier. You see here in the picture, so we have the reactant and product. It is getting, reactant is getting converted into the product. And at this point, the complex is getting, the reactants are getting activated and the complex is said to be the activated complex. Okay, and this point is nothing but the transition state. This point is called as the transition state. So this much amount of energy is required, okay, for the reactant to get activated. Now coming to the effective collision for bimolecular elementary reaction. So collisions with sufficient kinetic energy is needed and collision with proper orientation is needed. Okay. And we are getting one more equation which is K is equal to PZ e power minus EA by RT. So a new term P and Z is involved. Okay. We already know what is Z. Z is nothing but collision frequency, right? Z is nothing but collision frequency, and P denotes the steric factor or the probability factor. Steric factor or probability. Probability for the two molecules to get collided with each other. So that is denoted by the letter P. Okay, so it comes from proper orientation. So this equation is written in the form of Arrhenius equation where k is equal to a into e power minus a by rt. So instead of a, we have p z here in this equation. Got it? So where a is equal to pz is called frequency or pre-exponential factor. Pre-exponential factor. So with this, the lesson is getting over. So we'll try to solve some MCQs. We'll do some 1 or 2 MCQs from this topic and then we will wrap it up till today's session. Okay. So the first question is, which of the following affects the rate of the reaction? Collision frequency, effective collision, both A and B, none of these. What is the answer for this question? Option C.
Both
Good.
A and B.
Yes, yes. So both A and B. Option C is the correct answer. Very good. So thank you so much for listening the lecture, and here we are closing chemical kinetics lesson. Okay, so we have studied many topics from this lesson, and tomorrow we can solve some questions. Tomorrow we can solve some questions from this lesson. Okay, we can solve all the numericals part. Okay, from all the topics that we have studied from this lesson, because this lesson is a physical chemistry lesson where you get theory question as well as numericals. So you have to practice at least one numerical every day. Okay. So tomorrow we will try to solve some questions from this part, and later on you can practice those questions and you can solve questions similar to the questions which I am solving in the class. Okay, from your book, from your question solving books. So, okay. Clear, students? So do you have any doubts from chemical kinetics lesson? So study the lesson, study your book. So go through the notes that you have taken during the class every day, and see you all in tomorrow's session. If you're having any doubt, you can ask me. If there is no doubt, okay. Then we can meet up in the. Ma'am, how can I get the notes of these chapter? Okay, Aisha have joined today only, no? So Aisha, what you do? We have a channel like Avanti Live 2. Okay, Avanti Live 2 YouTube channel. So if you type Avanti Live 2 in the YouTube, you will get the videos, okay, from all the topics from all the lessons that I have discussed in this year. Okay, so we have completed 3 chapters: solutions, electrochemistry, and chemical kinetics. You can get all the videos, okay, from that page. Clear? Okay. Okay, students, thank you. Thank you so much. Take care. Bye-bye.